Before we begin, it's important to note, what you're about to hear are scientific paradoxes and thought experiments. They belong to the world of physics and philosophy, not faith. They don't replace religious beliefs, nor do they claim to explain the unseen. They are simply puzzles that scientists use to explore the limits of their theories. What if the universe isn't as solid as it feels? What if the ground beneath your feet, the light shining into your eyes, and even the flow of time itself are nothing more than shadows of a deeper, stranger reality? For centuries, science has promised us order, a world ruled by cause and effect, by laws as steady as gravity. But hidden beneath that surface is something unsettling, cracks in the very story of reality. And the more closely we look, the wider those cracks grow. Everyday life feels predictable. Drop a glass and it shatters. Flick a switch and the light turns on. The chain of events appears unbreakable, action followed by reaction, effect after cause. For most of human history, this was enough. Newton mapped the heavens with equations, Einstein reshaped our picture of space and time, and for a moment it seemed we had the universe pinned down. But the deeper scientists dug, the smaller the scales they studied, the more reality itself began to rebel. At the heart of this rebellion lies quantum mechanics, the most successful yet most mysterious framework in science. Its equations describe the hidden world of atoms, electrons, and photons with astonishing accuracy. Every computer chip, every laser beam, every MRI machine depends on it. But despite its triumphs, quantum mechanics conceals a truth that unsettles even the brightest minds. The rules work, yet no one truly understands why. And when we push those rules, they yield something far stranger than just complexity. They reveal paradoxes, not puzzles you solve on a rainy afternoon, but fractures in reality itself. In philosophy, a paradox is a riddle, something amusing or clever. In quantum physics, a paradox is a signal flare, a warning that something fundamental about our picture of the universe doesn't add up. These aren't trivial glitches. They are contradictions at the foundation of existence, the kind that make scientists lose sleep. Think of it this way, you're holding a phone. It works perfectly, sends messages, streams videos, never fails. But every so often, for no reason, the screen flickers with symbols no one can explain. The device still functions, but the anomaly hints at something deeper, a hidden flaw, or perhaps an entirely different operating system at work. That is what quantum paradoxes are, symbols flashing at the edge of our understanding, reminders that the universe may be stranger than anything we've dared to imagine. Scientists have tried to plaster over these cracks with interpretations, each more exotic than the last. Some insist that particles split into countless versions of reality. Others argue that consciousness itself is part of the machinery that chooses an outcome. Still others believe time doesn't flow as we think, that the future might already exist, tugging at the present. None of these answers sit comfortably, and none have one universal agreement. Yet all arise from experiments that are real, repeated, and verified. That is why these paradoxes matter. They are not philosophical musings but experimental facts, staring us down like riddles whispered by the universe. And each paradox is not just a puzzle to solve, but a guidepost pointing toward something bigger, a deeper theory, a new way of understanding reality itself. In the chapters ahead, we will journey through the most haunting paradoxes of the quantum world, experiments that suggest your choices can alter the past, thought experiments that question whether two people can live in different realities, puzzles that blur the line between time and causality, life and death, truth and illusion. These paradoxes terrify scientists not because they are unsolvable, but because they force us to confront the possibility that the universe doesn't play by rules we can fully grasp. And so we begin, at the edge of the familiar, staring into the cracks where certainty ends and mystery begins. Imagine rolling dice, not once, but forever, and only sometimes knowing why they land the way they do. That is the difference between the world we think we live in and the world science discovered when it dug deeper. The first is classical, predictable, almost mechanical. The second is quantum, a place where certainty evaporates and all that remains are probabilities. To grasp why quantum paradoxes shake the very ground beneath us, we first need to understand how sharply they contrast with everything that came before. Classical physics is built on the promise of determinism. In the 17th century, Isaac Newton showed that the same force making apples fall also governs the orbits of planets. The universe seemed like an intricate clock, every gear meshing with precision. If you knew the starting conditions, the weight of the apple, the height of the tree, the pull of gravity, you could predict exactly where and when it would hit the ground. This wasn't just philosophy, it was law. Action led to reaction, cause to effect, with no gaps in between. Centuries later, Albert Einstein reshaped this clockwork universe into something more elegant but no less predictable. Space and time bent under the weight of matter, light curved around stars, and the cosmos unfolded according to equations of breathtaking clarity. Relativity showed us that reality was stranger than Newton imagined. Time could stretch, space could curve, but it still obeyed logic. If you had complete information, you could in principle calculate the past, the present, and the future. The laws of nature allowed no uncertainty, no room for chance. Then scientists turned their gaze to the invisible, atoms, electrons, photons. They expected the same clockwork precision, only smaller. Instead, the machinery of the universe seemed to come apart. In the realm of the very small, particles did not behave like tiny billiard balls rolling along predictable paths. They flickered, blurred, and refused to be pinned down. An electron was not here or there but smeared across possibilities. A photon acted like both wave and particle, as if undecided about its own identity. The shock was not just that scientists didn't know enough variables. It was that even with perfect knowledge, the rules refused to allow certainty. The universe itself seemed to run on probabilities, not guarantees. Quantum mechanics was born, not out of choice, but out of necessity, a desperate attempt to make sense of a reality that had broken free of classical logic. Under this new framework, the universe no longer said, "This will happen." Instead, it whispered, "This might happen, with this chance." A particle may be here with 30% probability, there with 70%, and only when observed does one possibility crystallize into reality. It was as if the universe rolled dice for every event, and no one could say for certain which side would show. To most of us, probability is a matter of ignorance, like flipping a coin when we don't know which way it will fall. But in quantum physics, probability is not ignorance, it is the very fabric of reality. Even the most carefully designed experiments, repeated a million times, reveal not certainties but distributions. That shift, from determinism to probability, was nothing short of revolutionary. And with it came unease. If the future cannot be calculated with certainty, if events are not determined until the very moment they are measured, what does that mean for the nature of reality? Is the universe incomplete, hiding deeper laws we have yet to uncover? Or is randomness itself fundamental, woven into the structure of existence? This uncertainty is more than a technical nuisance. It tears at the foundation of science itself. For centuries, the goal of physics was to explain why things happen. Quantum mechanics changed the question. It no longer asks why this outcome, but only what are the odds. The answers work, they build our computers and satellites, but they leave us staring at a gap between description and meaning. That gap is where paradoxes thrive. They arise when probabilities meet our need for causality, when outcomes defy the simple chains of logic we trust. Paradoxes are the collisions between the old certainty of Newton and Einstein and the new uncertainty of the quantum world. They remind us that beneath every stable surface lies turbulence we cannot yet tame. And so, before we confront the strangest paradoxes themselves, we must carry this truth: the universe may not be a clock, but a casino. A place where dice roll endlessly, where chance is not illusion but law, and where certainty may be nothing more than a story we tell ourselves to feel safe. When does reality decide to be real? Is it when a machine records the data, or when you finally glance at the result? Is it when photons strike a detector, or only when a conscious mind becomes aware of them? These questions lie at the heart of one of the strangest and most unsettling puzzles in all of science, the measurement problem. To see why it matters, imagine an electron. In the classical world, it would be a tiny speck orbiting an atom like a planet around a star. You could point to its position, trace its path, and predict where it would be tomorrow. But in the quantum world, that certainty evaporates. The electron does not exist in one place. Instead, it exists in a state called superposition, a cloud of probabilities, as if it is in many positions at once. Mathematically, this is described by the wave function, an elegant equation that holds every possible outcome. Superposition is not just a trick of language. Experiments confirm it again and again. Particles interfere with themselves, behave like waves, and act as if they occupy multiple realities simultaneously. But then comes the moment of measurement. When you check the electron's position, the cloud collapses into one result. Out of countless possibilities, only one survives. And here lies the paradox: what decides which reality becomes the reality? The equations of quantum mechanics predict probabilities perfectly. They can tell you the odds with extraordinary accuracy. But they do not explain the act of collapse. They say nothing about the line between possibility and actuality. They leave us in a limbo where reality itself feels incomplete. Scientists have tried to draw that line in many ways, each spawning an interpretation of quantum mechanics, none entirely satisfying. The first and most famous is the Copenhagen interpretation, championed by Niels Bohr. In this view, quantum systems do not have definite properties until they are observed. The act of measurement forces the wave function to collapse. Before you look, the electron is spread out, a ghost of possibilities. The moment you measure, it becomes real. This interpretation preserves the math and matches the experiments. But it never defines what counts as a measurement. Is a Geiger counter enough? A computer display? Or does it require a conscious observer? The Copenhagen school left those questions deliberately vague, as if reality itself refused to be pinned down. Then came an audacious alternative, the many-worlds interpretation. Proposed by Hugh Everett in the 1950s, it rejects collapse altogether. The wave function never shrinks. Instead, every possibility happens. When you measure the electron, the universe splits. In one branch, the electron is here. In another, it is there. You, too, split into versions that witness each outcome. According to this view, reality is a constantly branching tree of worlds, each as real as the one you occupy. Many worlds avoids the ambiguity of collapse, but raises a haunting question: if every possibility exists, why do you experience only one? What singles out this version of you, in this universe, seeing this result? Others turn to a subtler approach, decoherence. In this view, collapse is an illusion created by interaction. A quantum system in superposition becomes entangled with its environment, air molecules, light, detectors. That entanglement destroys the delicate interference patterns and makes the system behave classically. Decoherence explains why quantum weirdness disappears as systems get larger. A cat may start as both alive and dead, but the environment forces one outcome to dominate. Decoherence has the advantage of matching experiments without invoking parallel universes. But it still does not answer the deepest question: why do we experience a single outcome? Why does one possibility become real instead of remaining a blur? Some interpretations go further, proposing objective collapse theories. These suggest that superposition is not eternal. Large systems cannot remain in quantum limbo forever. At some critical scale, the wave function collapses on its own, without measurement, like a decaying atom that eventually emits radiation. Collapse, in this view, is a physical process, not just an illusion of observation. But no one has yet detected such a collapse in action. The mechanism remains hypothetical, and the mystery persists. And then there is the most controversial idea of all, that consciousness itself plays a role. Some physicists, uncomfortable with the vagueness of measurement, suggest that the mind is not just a passive observer but an active participant. Reality becomes definite only when it enters awareness. This notion unsettles many scientists, who see it as smuggling mysticism into physics. Yet it lingers, because no alternative has fully explained why observation matters at all. The measurement problem is not a fringe debate. It is the central paradox of quantum mechanics. Every paradox we will encounter, particles behaving differently when observed, choices affecting the past, realities splitting between observers, all trace their roots back to this question. How does possibility become actuality? Without an answer, we are left with equations that predict perfectly but explain nothing. This is why Richard Feynman once quipped, "Nobody understands quantum mechanics." It was not a confession of ignorance but an admission of the paradox at its core. The mathematics works. The technology thrives. But the meaning eludes us. Reality itself seems to flicker, undecided, until the moment we look. The measurement problem matters because it is not just about electrons and photons. It is about the nature of existence. If reality waits for us to measure it, then we are part of the machinery of the universe, not separate from it. If reality splits into many worlds, then there are versions of us we will never meet. If consciousness collapses the wave function, then the observer is as fundamental as the observed. No answer yet commands agreement. Each interpretation solves part of the puzzle but creates new ones. Copenhagen explains the rules but leaves us with vagueness. Many worlds preserves the math but multiplies realities beyond comprehension. Decoherence matches experiments but sidesteps the core mystery. Collapse theories are bold but unproven. Consciousness remains unsettling, hovering at the edge of science and philosophy. And so the paradox endures, like a shadow we cannot shake. Measurement is not just a reading on a dial. It is the moment when the universe decides what is real. Or perhaps, the moment when we do. What if your decision today rewrote what a particle did yesterday? Begin with a single photon leaving its source and approaching a device that offers two paths. If nothing in the setup records which path it takes, the photon behaves like a wave, it explores both options at once. Many such photons build an interference pattern of alternating bright and dark bands. That pattern is the footprint of superposition, the signature of a story not yet decided. For a moment, the world postpones commitment and lets possibilities coexist. Now change the arrangement. The source produces twin photons linked by entanglement. One, the signal, flies to a position detector that stamps where it lands. The other, the idler, passes mirrors and beam splitters to a device with two modes. In one mode, the idler will carry reliable witchpath information about the signal. In the other, its paths recombine so that no witchpath clue survives. Crucially, the signal reaches its detector first. Your decision about the idler comes later, after the signals is already recorded. Consider the first mode. If the idler's route preserves witchpath information, the experiment holds a record that could distinguish the signal's path. When such a record exists, the phase relationships that create fringes are destroyed. When you pair each signal detection with its idler detection, the subset of earlier signal hits associated with path knowledge forms a smooth, hill-shaped distribution. No ripples. The statistics tell a particle-like story. The photon behaved as if it chose one route and stuck to it. Now choose the second mode. Route the idler so its paths recombine and any witchpath clue is erased. You cannot, even in principle, tell where it came from. Later, sort the already recorded signal positions by the idler's outcomes. One subset of earlier dots forms fringes, a complementary subset forms anti-fringes shifted by half a period. Sum them and the stripes cancel, leaving a blur, but within the subsets the wave-like texture is clear. Data written before the choice seem to reveal interference after the fact. The temporal order is the sting. The signal positions were stored before the idler setting was chosen, yet the statistical texture of those earlier positions depends on the later decision to keep or erase path information. It feels like a hand reaching backward, choosing which path makes sense. Still, it cannot send messages. The unsorted signal pattern carries no clue about any future setting. Only after coincidence counting, pairing each signal event with its partner idler event, do fringes appear within the proper subsets. No faster-than-light whisper, only correlations. Nothing travels faster than light, and no one writes to yesterday, yet a later choice sets the meaning of fixed past records. What, then, is being rewritten? Think of the whole apparatus: source, paths, detectors, and settings as one indivisible experiment. Quantum facts are tiles in a mosaic whose image appears only when the tiles are arranged together. With path information, the consistent mosaic is particle-like. With erasure, it is wave-like. The past was underdescribed, not undone. The later choice selects the story those earlier dots can join without contradiction. Different interpretations tell this story in different accents. In a Copenhagen-style view, the measurement context decides which questions have definite answers. The later setting is a declaration: path information matters, or path information is meaningless, and the statistics comply. Decoherence rephrases it: entanglement with any would-be record spoils phase coherence and wipes out fringes, while erasure prevents the environment from distinguishing the alternatives, letting coherence reappear in the sorted sub-ensembles. The raw screen shows no stripes because complementary fringes cancel, meaning lives in correlations. Many Worlds offers another translation: there is no collapse, only branching into consistent histories. The joint system evolves into branches with path knowledge and branches without it. Your later setting correlates you with a particular branch and determines how you sort earlier records. What looks retroactive is simply discovering which branch you occupy. Time-symmetric approaches go further. They treat the experiment as bounded by preparation and post-selection, with influences from past and future alike. On that view, the later idler choice supplies a boundary condition that lets earlier signal data acquire structure. Whichever lens you choose, the intuition that facts are local and sequential feels inadequate. The delayed choice quantum eraser shows that facts are relational, stitched across space and time by correlations. A dot on the screen is only a dot until paired with its partner outcome, then it joins a pattern with character. The lesson is not that effects precede causes, but that cause and effect are knotted threads in a larger tapestry, where meaning crystallizes only when the whole weave is seen. That realization unsettles more than causality. It challenges explanation itself. We want the world to answer what happened, with a single, self-contained account. Here, the world answers with a conditional: tell me which question you are asking, and I will show you the past that fits. We do not edit history, we choose the key that unlocks one of its consistent melodies. Once you hear it, the silence between notes sounds different, as if possibility had always been part of the song. What if your decision today rewrote what a particle did yesterday? The experiment replies with a quieter claim: your decision today helps decide which past becomes legible. For many, that is disquieting enough, and it is only the beginning of where quantum paradoxes lead. What if you and I saw the same event, and we were both right, but reality itself disagreed? This is not a riddle about perception or memory. It is one of the deepest cracks in the foundations of physics, a thought experiment known as Wigner's friend. It takes the familiar strangeness of Schrödinger's cat and sharpens it into something personal, unsettling, and nearly impossible to ignore. Imagine a laboratory sealed from the outside. Inside is Wigner's friend, performing a measurement on a quantum system, say, a particle in superposition, spin up and spin down at once. The friend activates the apparatus, observes the result, and writes it down. From their perspective, the ambiguity ends. The wave function collapses, and the particle reveals itself, spin up. At that instant, the friend inhabits a world with a definite outcome, no paradox in sight. Now shift the frame. Wigner himself stands outside, unaware of the friend's observation. To him, the laboratory, the friend, and the particle together form a single quantum system. Since he has not opened the door, he must treat the entire lab as being in superposition. Inside, the friend has seen spin up. But in Wigner's description, the friend is entangled, and one branch having seen spin up, and another having seen spin down. The paradox is sharp. Both accounts are consistent with quantum mechanics, yet they cannot both describe a single, objective reality. So who is right? The friend, who insists the outcome is definite? Or Wigner, who insists the lab is still suspended in probabilities? If we take both seriously, the answer seems to be, both are right, but their truths are incompatible. For decades, this remained a thought experiment, a kind of quantum fable meant to highlight the oddities of measurement. Critics dismissed it as fanciful. After all, how could a human being ever exist in superposition? But technology advanced, and physicists learned to test simplified versions with photons, ions, and detectors. In 2019, a landmark study published in Nature Communications created a scenario resembling Wigner's friend using entangled particles. Two separate observers recorded outcomes that, when compared, amounted to different versions of reality. The unsettling conclusion: under quantum rules, it is possible for two observers to experience the same event differently, and for both accounts to be correct within their own frame. The implications are staggering. In classical physics, disagreements between observers mean someone is mistaken. Reality is assumed to be singular and objective, even if human perception falters. In quantum physics, Wigner's friend suggests otherwise. Reality may not be a single stage where events unfold identically for all. Instead, it may fracture into perspectives, each internally consistent but irreconcilable with the others. One interpretation embraces this directly: the many-worlds view. Here, when the friend makes a measurement, reality branches. In one world, they see spin up, in another, spin down. Wigner, outside, remains entangled with both until he interacts with the lab. When he does, he, too, branches, aligning with one outcome or the other. In this picture, there is no contradiction because each observer simply occupies a different branch. Both are right, but in different universes. Other interpretations take a subtler approach. Perhaps measurement is not about collapse but about updating information. The friend updates their knowledge when they observe spin-up. Wigner, lacking that information, must describe the lab as still uncertain. The paradox then becomes one of perspective, not multiple realities, but multiple descriptions. Yet this solution falters when observers compare notes. If reality is only relative knowledge, why should their accounts agree when they finally meet? What ensures consistency? The paradox does not fade under scrutiny, it grows deeper. At stake is the very notion of objectivity. Can we still speak of an event as really happening if it may be different depending on who observed it? Is truth something shared, or something personal? Wigner's friend does not answer, it only sharpens the dilemma. Imagine extending it beyond the lab. Two people watch the same coin toss. One swears it landed heads, the other insists on tails. In our ordinary world, at least one is mistaken. In the quantum world implied by Wigner's friend, both may be correct, but in different slices of reality. The unsettling part is that there may be no overarching truth to reconcile their stories. Reality itself could be fractured, observer-dependent, plural. Some physicists recoil at this possibility, searching instead for hidden variables or deeper rules that restore objectivity. Others embrace it, suggesting that reality as we know it may not exist independently of observation. Each observer, they argue, may inhabit their own private slice of the universe. Both positions leave us uneasy. One risks overturning the structure of quantum mechanics, the other risks unraveling the very idea of shared truth. That is why Wigner's friend terrifies scientists. It is not just about particles or wave functions. It is about what it means to say something happened. It asks whether reality exists outside our perception, or whether each observer is locked into their own unfolding world. If truth itself can be relative at the quantum level, then the universe may be stranger than even paradox can capture. What if the future is already shaping your past? The question sounds like philosophy or science fiction, but in quantum mechanics it becomes a real possibility, a paradox drawn not from imagination but from equations and experiments. We grow up believing that time is an arrow. The past lies behind us, the present unfolds beneath our feet, and the future stretches forward, unwritten. Cause comes first, effect follows. Drop a glass, then hear it shatter. Plant a seed, then watch it grow. This one-way progression is so deeply ingrained that it feels like common sense. Yet the mathematics of quantum mechanics tells a different story. At its core lies time symmetry. The fundamental equations, including Schrödinger's equation, which governs how quantum systems evolve, work just as well forward as backward. Flip the timeline, and the math still fits. To the equations, there is no preferred direction. What we call the arrow of time seems to be absent at the most fundamental level. That alone is unsettling. But quantum experiments go further, hinting that events in the future might actually influence what happens in the past. One of the clearest examples is the delayed choice quantum eraser experiment. As we saw earlier, the decision to keep or erase information about a photon's path, made after the photon has already hit a screen, determines whether an interference pattern appears in the data. The pattern does not emerge until we sort results based on that later choice. It feels as though the photon's earlier behavior depended on a decision made afterward. Physicists are careful here. This is not time travel, nor does it allow anyone to send messages to the past. No experiment has ever shown a way to rewrite history or warn your younger self. But the correlations remain troubling. They suggest that the neat chain of cause-preceding effect may not be absolute. The quantum world resists our demand for chronological order. Some interpretations take this seriously. Among them is the two-state vector formalism, developed in the 1960s by Yakir Aharonov and colleagues. It describes a quantum system not just with a state evolving forward from the past, but with a second state evolving backward from the future. The present, in this picture, is shaped by both boundary conditions, what was true at the beginning and what will be true at the end. Reality becomes a meeting point between influences traveling in both directions. Imagine reading a book where the meaning of chapter 1 depends on how the final chapter concludes. Retrocausal models propose that quantum events are like that, incomplete until both past and future are considered. The story cannot be told from one end alone. This dovetails with another radical idea known as the block universe. According to Einstein's relativity, time is woven with space into a four-dimensional fabric called spacetime. In this view, the past, present, and future all coexist as parts of a single, unchanging structure. We do not move through time like a train along a track. Instead, we inhabit different slices of the block. The flow of time, so vivid in our experience, may be an illusion born from consciousness. If the block universe is real, then the future already exists as surely as the past. Retrocausality fits naturally here. The future can shape the present because it is already there, a fixed part of the whole. From this perspective, free will begins to look fragile. Are our choices genuinely ours, or are they predetermined threads in the block, giving only the illusion of spontaneity? The psychological unease is hard to overstate. We are creatures of the arrow. Our lives are built on before and after, cause and effect. Responsibility, memory, and meaning depend on it. To suggest that the future already plays a role in shaping the present threatens not only physics but identity itself. If tomorrow's boundary conditions help decide today's outcomes, then the line between choosing and being carried by inevitability blurs. And yet, some scientists see comfort here. Retrocausal interpretations can resolve thorny paradoxes without invoking multiple universes or mystical collapse. They restore symmetry to the equations and smooth over the discontinuity of measurement. Instead of reality snapping into place when observed, the picture is of a world woven seamlessly from both ends of time. Still, critics argue that such views come at a heavy cost. They risk undermining our sense of agency. If future events are already written, what does it mean to act, to decide, to change? Does free will survive in a block universe where every choice is a fixed fact and every branching possibility is merely an illusion? Perhaps the deeper truth lies between perspectives. On human scales, time feels irreversible. Entropy increases, glasses shatter but never reassemble, lives move forward. These are the signatures of a macroscopic arrow emerging from countless microscopic events. But at the quantum level, where paradox thrives, the arrow bends. There, past and future may not be separate but entangled, their influences overlapping in ways we can barely grasp. This tension, between the time we live and the time physics describes, is why retrocausality unsettles so deeply. It tells us the most basic feature of our world, the flow of time itself, may not be fundamental. The universe might not march forward step by step. It may be a network of events, stitched together across directions, with the present forever shaped by both what has been and what is yet to come. What if the future is already shaping your past? The experiments cannot yet answer. But they whisper that the line we draw between then and now, between memory and anticipation, may not be written in the universe itself. It may only be written in us. What if you and a stranger could win every game without ever speaking? No whispers, no signals, no strategy sessions, and yet every time the score is tallied, you both come out flawless. In the ordinary world, this is impossible, a dream of perfect coordination without communication. But in the quantum world, it is not only possible, it has been demonstrated. Physicists call it quantum pseudo-telepathy, an illusion of mind reading born not from magic, but from entanglement. Imagine a game. You and a partner are placed in separate rooms. You cannot talk, write, or share messages of any kind. A referee asks each of you a question drawn at random from a list. Your task is simple: provide yes or no answers that satisfy certain rules when compared at the end. In the classical world, you could try to agree on a strategy beforehand, memorizing an enormous chart of possible questions and answers. But no matter how clever your preparation, there will always be combinations you cannot handle. At best, you might win most of the time, but never perfectly. Enter quantum entanglement. Before the game begins, you and your partner are each given one half of an entangled pair of particles. These particles share a connection so profound that they are not two independent objects but one system, spread across distance. When you measure your particle, its outcome is instantly correlated with your partner's, no matter how far apart you are. Neither of you sends a signal. Neither cheats. Yet when the answers are compared, they align in ways no classical system could explain. To an outsider, it looks like telepathy. One of the clearest examples is the magic square game. It involves a 3x3 grid filled with +1s and 1s. The challenge is that your row must multiply to +1, while your partner's column must multiply to -1. At the intersection cell, your answers must match. In the classical world, no predetermined chart can guarantee success every round. The rules are too strict, contradictions eventually arise. But with entanglement, players can perform quantum measurements that guarantee perfect coordination every time. Their answers are not prearranged but drawn from the deep correlations embedded in the shared quantum state. Another striking case is the GHZ game, named after physicists Greenberger, Horn, and Zeilinger. This involves 3 players, each asked questions with yes or no answers. The rules demand a pattern of responses impossible to satisfy with classical strategies. Yet with entangled particles, the trio can coordinate perfectly. They win not by exchanging signals but by tapping into correlations that classical logic cannot reproduce. The power of pseudo-telepathy lies not in sending information but in eliminating the need for it. Classical players must communicate to guarantee coordination, but quantum players already share outcomes through entanglement. Nothing travels faster than light. No secret message passes between them. Instead, the entangled system behaves as if separated individuals are still pieces of a single whole. Einstein famously derided this as spooky action at a distance. He believed entanglement revealed that quantum mechanics was incomplete, a placeholder until hidden variables restored sanity. But repeated experiments, from Bell's theorem tests in the 1970s to loophole-free demonstrations in the 21st century, have confirmed that entanglement is real and stronger than Einstein suspected. The pseudo-telepathy games are just playful demonstrations of a deeper truth: the world cannot be both local and realistic. Locality means that effects cannot travel faster than light. Realism means that physical properties exist before they are measured. Entanglement forces us to abandon at least one. If we keep locality, we must accept that measurement outcomes are not predetermined, they emerge only when observed. If we keep realism, we must accept that information travels instantaneously across space. Either way, the classical picture collapses. The implications ripple far beyond games. Quantum pseudo-telepathy highlights a universe where connection transcends distance. 2 particles on opposite sides of the galaxy, once entangled, behave as if distance does not matter. 2 people playing a game, once linked through entanglement, can coordinate without communication. The rules of cause and effect, so solid in daily life, bend in ways that strain intuition. And yet, even here, there are limits. Pseudo-telepathy does not allow you to send a secret message to your partner faster than light. The correlations emerge only when the results are compared afterward. It is not a telephone to the stars, but a reminder that the universe may be stitched together at a level beyond space and time. Philosophically, this leaves us staring at the foundations of reality. What does it mean to say two things are separate if they can behave as one? What does it mean to say properties exist independently if they only appear when measured? Entanglement unsettles not just physics but ontology, the very idea of what is. Quantum pseudo-telepathy dramatizes this tension. It is playful on the surface, a puzzle about winning games. But beneath the surface lies the larger question: do we inhabit a universe of independent objects bound by distance, or a universe of hidden wholeness where separation is an illusion? The answer remains elusive. But the games whisper a message: the universe is stranger than we dreamed, and what looks like telepathy may be nothing more than reality revealing its deeper connections. What if a particle could leave its own properties behind? Imagine watching a cat walk through a corridor, only to see its grin wander down one path while the rest of its body slips down another. This is the metaphor physicists use when they describe one of the strangest quantum experiments ever performed, the quantum Cheshire cat. The story begins with neutrons, particles found inside every atom. Neutrons possess both a position and a property called spin, which describes their built-in quantum orientation. In our everyday intuition, an object carries its properties wherever it goes. A spinning top does not leave its rotation behind when you move it. Heat does not separate from a flame. Yet the quantum Cheshire cat experiment challenges this most basic assumption. In the laboratory, scientists directed neutrons into an interferometer, a device that splits their paths like a fork in the road. At first, the neutrons occupy both paths in superposition, spread across possibilities until a measurement is made. Then researchers performed a subtle trick. They designed the apparatus so that the neutron's position was probed in one path, while its spin was probed in the other. Instead of forcing the particle to choose a single path, they used a method called weak measurement, which allows researchers to extract partial information without fully collapsing the quantum state. The results were startling. The measurements behaved as though the neutrons traveled primarily down one arm of the interferometer, while their spin appeared in the other. In effect, the particle and one of its defining properties had become separated. The body went left, the grin went right. How can this be? Classical intuition insists that an object is a bundle of traits bound together. Position, spin, charge, and mass all move as a unit. The quantum Cheshire cat experiment suggests otherwise. In the quantum realm, properties may be more fluid, detachable, and context-dependent than we imagined. Skeptics argue that nothing literally splits. They point out that weak measurement is statistical, a gentle probe that reveals average tendencies across many trials rather than definitive outcomes in single events. According to this view, the neutron and its spin never parted ways. What we see is an illusion born of probabilities, not a cat without a grin. But others take the result more seriously. They argue that the experiment highlights a fundamental truth: quantum objects are not like classical things. They are not tiny balls carrying permanent attributes. Instead, they are clouds of potentialities, with properties that only crystallize in response to measurement. In one setup, position and spin appear together. In another, they seem to drift apart. Reality, in this telling, is not absolute but conditional, molded by the context in which it is observed. The philosophical weight of this paradox is enormous. What does it mean to call something an object if its properties can peel away? If a neutron can be detected without its spin, then perhaps what we think of as things are not solid entities but temporary constellations of attributes. Position here, spin there, charge waiting to emerge elsewhere, all bound together not by necessity, but by interaction. The quantum Cheshire cat also connects to the larger measurement problem. Once again, reality resists being pinned down until we look. The neutron does not carry its properties like luggage. Instead, the act of measurement decides which features appear, and sometimes where they appear. It is not just that observation reveals reality, observation seems to create the very story we tell about what happened. This is why the grin without the cat unsettles so deeply. It is more than a laboratory curiosity. It is a challenge to the categories by which we make sense of the world. We are accustomed to thinking that identity is stable, that objects are bundles of traits inseparably bound. The quantum world replies, not always. Identity may be contextual, properties may be provisional, and what you see may depend as much on how you ask as on what is there. What if a particle could leave its own properties behind? The Cheshire Cat experiment whispers that this is not just fantasy but part of the strange logic of quantum mechanics. The grin without the cat is a reminder that reality is slippery, its features unfolding only when called forth, and sometimes wandering off on their own. From your own perspective, you may never actually die. The claim sounds absurd, but it emerges from a thought experiment so unsettling that many physicists prefer not to discuss it at all. It is called quantum suicide, and it grows out of the radical logic of the many worlds interpretation of quantum mechanics. Picture a sealed chamber, silent and isolated. Inside sits a person facing a device linked to a quantum trigger. The trigger relies on the spin of a particle, a property that has a 50-50 chance of being measured as up or down. If the result is spin up, the device does nothing. If the result is spin down, the device fires a gun. Each press of the button is a gamble with even odds, survival or death determined by quantum chance. From the outside, repeated trials look grim. Half the time, the observer dies. After enough runs, the likelihood of survival shrinks to nearly nothing. Any external witness sees what common sense predicts, tragedy repeated until only one outcome remains. But what about the person inside the box? Here the paradox blooms. According to the many worlds interpretation, every quantum outcome occurs, but in different branches of the universe. Each time the trigger is pulled, the cosmos splits. In one branch, the gun fires and consciousness ends. In another branch, the gun clicks harmlessly and the subject survives. For outside observers, both outcomes exist in parallel realities, though they can only witness one. From the subject's own perspective, however, the story is skewed. They never experience the branches in which they die, for obvious reasons. Instead, they find themselves continuing only in the branches where survival occurs. No matter how improbable, there is always at least one surviving branch, and consciousness follows it. To the person inside the box, every click of the trigger leads to survival. Again and again, against all odds, they remain alive. This is the essence of quantum immortality, not that one literally lives forever, but that subjective experience never ends. The mind always tracks the surviving path, however unlikely it becomes. The experiment ensures that from the first-person view, death is never encountered, because there is always a version of the self that continues. At first glance, this might sound like a promise of eternal life. What could be more comforting than the assurance that your awareness will never cease? Yet when examined closely, the idea curdles into something darker. For in practice, survival under such terms does not mean thriving. It means persisting in increasingly improbable worlds, wounded, isolated, or alone, while most other branches end. The odds grow stranger with each survival, until the only remaining worlds are bizarre, inhospitable, or nightmarishly unlikely. Immortality, in this sense, becomes a curse. Imagine surviving disasters that wipe out everyone else, persisting through catastrophes where your continued existence is the least probable outcome. You may never experience death, but what you do experience could be a dwindling corridor of improbable survival, stretched thinner and stranger with each step. The thought experiment suggests not triumph, but exile, condemned to endure when all natural odds said you should not. The paradox does not prove that consciousness leaps between branches. It does not establish that immortality is real. It simply explores the consequences if the many worlds interpretation is correct. And therein lies the unease. If the universe truly splits with every quantum event, then the logic of continuity seems unavoidable. Your awareness could only ever inhabit the branches where it still exists. Death would never be something you directly experience, only something that happens in branches you can no longer access. But what, then, does survival even mean? If countless versions of you already exist, and countless others die each instant, what makes your consciousness special? Why do you experience this particular line of continuity rather than another? The thought experiment forces us to confront the mystery of identity in a multiverse. Are you one among many, or are you simply the perspective tied to the branch that keeps surviving? These questions slide quickly from physics into philosophy, and even into dread. Quantum suicide highlights not just the strangeness of many worlds, but also the limits of our understanding of consciousness. Physics can describe wave functions, probabilities, and branching universes. But it cannot yet say what awareness is, or why it seems to follow one path instead of another. The thought experiment does not answer the riddle. It only magnifies it. And so we are left with a disturbing vision. From the outside, life looks finite, bounded by chance and decay. From the inside, if many worlds is true, life may be endless, but not in the way we hope. It is not immortality as reward, but survival as inevitability, dragging us forward into worlds stranger and lonelier with every step. From your own perspective, you may never actually die. Whether that thought is comforting or horrifying depends on how long you are willing to live with the possibility. What if the universe's darkest objects were hiding its deepest secret, that information itself can die? This is the heart of the black hole information paradox, one of the most profound clashes in all of physics, a rift that pits Einstein's general relativity against the strange laws of quantum mechanics. Black holes have always invited awe. They are the collapsed corpses of massive stars, places where gravity grows so strong that space and time themselves are warped into submission. Cross the event horizon, the invisible boundary surrounding a black hole, and escape becomes impossible. Not even light can flee. To the outside world, the black hole appears as a silent shadow, a region cut off from the rest of existence. According to Einstein's relativity, black holes are simple creatures. They can be fully described by just three numbers: mass, charge, and spin. Everything else, the complex patterns of atoms that fell in, the structure of stars, even the traces of matter that formed them, is erased. Physicists call this the no-hair theorem. Black holes have no distinguishing features. They forget the details of what created them. But quantum mechanics does not forgive so easily. In the quantum world, information is sacred. It cannot be destroyed. Every process, no matter how chaotic, scrambles information but preserves it in principle. If you burn a book, the words vanish from sight, but in theory, the positions of the ashes, the heat of the smoke, and the motion of the molecules still encode the story. Information may scatter, but it never disappears. This principle is woven into the very mathematics of quantum theory. Without it, probabilities would not add up. So what happens when something falls into a black hole? Relativity says the details vanish forever. Quantum mechanics says the details must remain. Two of the most successful theories in science stare each other down, and both cannot be right. The paradox deepened in the 1970s, when Stephen Hawking discovered that black holes are not entirely black. Using quantum field theory, Hawking showed that pairs of particles can spontaneously appear near the event horizon. One particle falls in, the other escapes. To an outside observer, the black hole appears to glow faintly, radiating energy now called Hawking radiation. Over immense timescales, this process drains the black hole's mass until it eventually evaporates completely. At first, this seemed like a triumph. Black holes were not eternal prisons, they slowly leaked energy back into the cosmos. But there was a catch. Hawking's calculations showed that the radiation was featureless, carrying no imprint of what had fallen inside. If the black hole eventually disappears into nothing but random radiation, then all information about what it once contained is lost forever. Quantum mechanics screams that this cannot happen, yet relativity insists that it must. This is the black hole information paradox, the two great pillars of physics not merely disagreeing but openly contradicting each other. It is as though the universe is written in two languages that say opposite things about the same sentence. Physics itself appears at war with itself. Over the years, possible resolutions have emerged, each bold, each unsettling. One is the holographic principle, inspired by work in string theory. It suggests that everything falling into a black hole is somehow encoded on the event horizon, like information inscribed on a two-dimensional surface. Just as a hologram contains a three-dimensional image in a flat film, the event horizon could store the data of everything swallowed, releasing it later through subtle patterns in the Hawking radiation. If true, the paradox dissolves, the information never dies, it only hides. Even stranger, the holographic principle implies that perhaps the entire universe works this way, with three-dimensional reality emerging from a deeper two-dimensional layer of information. Another proposal is the firewall hypothesis. To preserve information, it suggests that the event horizon is not a smooth boundary, as relativity predicts, but a raging inferno of high-energy particles. Anything crossing it would be incinerated instantly. The firewall solves the information paradox, but at a terrible cost. It breaks Einstein's principle that falling into a black hole should feel no different until reaching the singularity. If firewalls are real, then relativity itself must be revised. Other approaches point to even deeper unknowns. Some physicists argue that information seeps out in delicate correlations hidden within the Hawking radiation, too subtle for current calculations to reveal. Others propose that space and time themselves are not fundamental but emergent, and that the paradox signals the need for an entirely new theory of quantum gravity. What makes the black hole information paradox so frightening is not simply the mystery of where the data goes. It is the way it exposes the limits of our knowledge. Relativity and quantum mechanics have been tested countless times and never failed. Yet place them together at the edge of a black hole, and they tear each other apart. It is as though the universe is daring us to admit that our most cherished theories are incomplete. Even today, no consensus exists. The holographic principle is elegant but unproven. The firewall is bold but radical. Other proposals remain speculative, each trading one piece of physics for another. The paradox endures, like a riddle whispered by the cosmos itself. What if the universe's darkest objects were hiding its deepest secret, that information itself can die? If that is true, then quantum mechanics must be rewritten. If it is false, then relativity must yield. Either way, black holes stand as monuments to our ignorance, their silent horizons concealing a truth so deep it may reshape the foundations of science. Maybe the universe isn't broken, maybe our story of it is. That is the hidden message behind every paradox we have explored. Each one is not a glitch to be dismissed but a crack in the wall, a place where the story we tell about reality no longer fits the facts we observe. And history shows us that cracks are often where revolutions begin. In Newton's age, the universe was a machine, predictable and precise. His laws explained falling apples and orbiting planets with a clarity that seemed final. Then came Einstein, showing that Newton's clockwork universe was only part of the story. Space and time bent under the weight of matter, and the cosmos revealed itself as a vast geometry. The wall cracked, and out of it came relativity. A generation later, another fracture appeared. On the smallest scales, particles refused to follow deterministic paths. They smeared into probabilities, collapsed under measurement, and entangled across distance. The wall cracked again, and from that rupture came quantum mechanics, stranger than anyone had imagined, yet precise enough to power the modern world. Now the paradoxes stand as new fractures, whispering that even quantum mechanics may not be the end of the story. The measurement problem tells us we still don't know when possibility becomes reality. The delayed choice quantum eraser unsettles causality, suggesting that the present and the past are more entangled than we admit. Wigner's friend raises the possibility of multiple realities coexisting side by side, each true in its own way. Retrocausality bends the arrow of time, hinting that the future may already play a role in the present. Pseudo-telepathy shows connections that defy locality, while the Cheshire Cat experiment peels apart objects from their own properties. Quantum suicide confronts us with the terrifying notion that consciousness may persist in improbable branches, and the black hole information paradox reminds us that our two greatest theories, relativity and quantum mechanics, are still at war. Taken together, these are not random curiosities. They are coordinates on a map leading us toward something deeper. Just as the cracks of the past pointed to revolutions, so too may these. They tell us the story of physics is not finished. What might come next? Perhaps a theory that unites gravity with quantum mechanics into a single framework of quantum gravity. Perhaps a view of the universe where space and time are not fundamental at all, but emergent, woven from information. Or perhaps something stranger still, a language we have not yet invented, one that explains why reality looks probabilistic, why measurement matters, and why paradox is everywhere. Paradoxes terrify scientists because they shake our foundations. But they also invite us forward. They remind us that certainty is often an illusion, and that discovery begins where comfort ends. The universe may not hand us answers, but it leaves us hints, riddles, contradictions, paradoxes. Each one a guidepost pointing to truths still hidden. So maybe the question is not whether the universe makes sense, but whether our stories are big enough to hold it. If history is any guide, the cracks we see today may be the openings through which tomorrow's science will emerge. As we close this journey through the strangest paradoxes of physics, remember, the awe, the unease, the mystery, these are not flaws in our understanding. They are invitations. They are the universe's way of telling us we are not done yet. And if you want to keep exploring those cracks with me, the questions that unsettle us, the mysteries that refuse easy answers, make sure to subscribe. Because the story of reality is still unfolding, and the next chapter might be stranger than anything we have imagined.